Cloud RAG sells your data twice. Local RAG ships in one file, same quality. Now, on to the AI learning.
This course is about sovereign RAG, local first retrieval systems you can actually ship. We will build production-grade pipelines in Python and TypeScript through the DDS Vibe Academy, using only tools you can run on hardware you control. And the entire curriculum is free. Sovereign architecture means your organization owns the entire data plane. All processing happens locally for full privacy. Open source primitives prevent vendor lock-in. And when the cloud is involved, you always bring your own key and define the terms of that interaction. Why local architecture? First, data residency and compliance often require offline processing. Second, once deployed, local queries and embeddings have effectively zero marginal cost. Third, model independence shields you from sudden API changes or model deprecations. Our retrieval stack has 5 core components. Embeddings convert text to vectors. A vector store provides a durable index. A retriever finds nearest neighbors. A reranker sorts by precision. And an LLM performs grounded generation. We wire each piece directly for full control. We must decide where each component runs. Local only is mandatory for embeddings and vector storage. A hybrid mode uses cloud models only for final generation. Cloud only is reserved for cases where local hardware cannot support the required context window. Ingest begins by loading documents from local disk and splitting them into overlapping character chunks. Using Ollama with the nomic-embed-text model, we embed each chunk locally. This keeps all tokens on your machine while preparing the corpus for retrieval. For storage, we rely on Postgres with the pgvector extension. We create a table with a 768-dimension vector column and insert both raw text chunks and their vectors. This gives us a robust, production-ready vector store without introducing a new database system. At query time, we embed the user's question with the same model used for the corpus. We then run a cosine distance search in pgvector and retrieve the top k most similar chunks. Using cosine similarity here is essential to preserve ranking quality. To generate answers with Claude, we inject the retrieved chunks directly into the prompt and instruct the model to answer only from that context. Using your own API key, the cloud model becomes a controlled generator, tightly bound to your local evidence. In TypeScript, Xenova's transformers.js lets us run nomic-embed-text entirely in Node. We generate normalized embeddings in memory without Python, enabling a fully local retrieval stack for JavaScript applications while staying within the existing ecosystem. We store vectors in LanceDB, operating natively on local disk from TypeScript. After connecting, we insert documents with IDs, text, and vectors. LanceDB infers the schema and persists everything. This keeps the retrieval pipeline lightweight and dependency-free. To retrieve top K chunks in TypeScript, we embed the user query locally, run a vector search against the LanceDB table, and limit results to a strict top K because vectors already live on disk. This retrieval step completes in just a few milliseconds. For grounded answers, we assemble a context window from the retrieved chunks and send it to Claude via the official TypeScript SDK. By constraining the model to this context, the API functions purely as a reasoning engine over your verified local data. Chunking strategy strongly influences quality. Fixed-size chunks are fast, but may split ideas. Semantic or section-based chunking, such as using markdown headers, yields better context at the cost of complexity. Tuning size and overlap often beats changing the model. Every chunk must carry mandatory metadata: its source, URI, page, nearest section header, a version hash of the content, and an embedded at timestamp. This schema enables deterministic re-embedding, precise updates, and reliable citation in generated answers. The 50-15 rule summarizes quality. Half of answer quality comes from retrieval mechanics, only 15% from the LLM itself, and the remaining 35% from chunking and metadata design. The model never learns your data. Retrieval precision sets the ceiling. Failure mode 1 is context collapse. The model misses facts that are present because top K is too high or chunks are too large, overflowing the context window. The remedy is to lower top K and tighten chunk sizes so key passages remain visible to the model. Failure mode 2 is embedding drift. Duplicate chunks appear when IDs are non-deterministic, or when the embedding model changes between indexing and querying. Fix this by hashing the source path for IDs and freezing the embedding model for the life of the index. Failure mode 3 is retrieval echo, where the model invents details not in the text. This occurs when prompts allow reliance on pre-trained knowledge and lack refusal rules. We must explicitly instruct the model to answer only from context or say it does not know. Before shipping, validate a 50-question evaluation set. Hit sub 300 millisecond retrieval. Enable an embedding cache and implement replay logs. If you can meet this checklist entirely offline, you have achieved true data sovereignty, and the curriculum remains free.